In this lesson, we're going to talk about combining probabilities. So what we mean by combining probabilities, if, for example, we have two events, A and B, and I want to find the probability that event A and event B happens, or I want to find the probability that event A or event B happens. So we're going to really focus on the and versus the or statements. Now, before we get into how to calculate those kinds of probabilities, the first thing we have to talk about is independent events versus dependent events. The way that we calculate the probabilities depends on whether or not the events are independent or dependent. So we have to understand the difference between those two first. So, two events are independent if the outcome of one event doesn't affect the probability of the second event. So an example of this would be flipping a coin. Let's say I flip a coin twice. And let's say the first time I flip the coin, I get a tail. Well, the outcome of the first flip is not going to affect the probability of getting a tail on the second flip. So those two events are independent. Two events are dependent if the outcome of one event does affect the probability of the second event. An example of dependent events is if I have a bucket of, say, 10 blue chips and 10 red chips. Now, the chances of pulling out a blue chip would be a half, because I have 10 blue chips and 10 red chips, so I would have 10 out of 20 chance of pulling out a blue chip if I randomly just pick out a chip from the bucket. And the same thing goes with red chips. If I pull out a red chip, the probability of that happening would be 1/2. Now, let's say I reach in that bucket and I pull out a blue chip. So that probability is 1/2. I pull out a blue chip. So now what's left in there, in the bucket, is 19 chips, 9 blue and 10 red. So now if I go in and try to reach in and pick another chip, the probability has now changed of whether I get, depending on whether I get a blue or a red chip. If I get a blue chip, that probability on the second pull would be 9 out of 19 now, because I only have 9 blue chips in there if I pull a blue one out the first time. The probability of getting a red chip is now 10 out of 19 instead of 10 out of 20. There's still 10 chips left in there, but out of a total of 19. So this probability has changed based on the first pick. So the event of the first pick has changed the probability or affected the probability of the second pick. So this is an example of dependent events. When we go to calculate probability of and statements, for example, the probability of an event A and B happening, we calculate that differently for events that are independent or events that are dependent. If the event is independent, then the probability of an event A and an event B happening is you just take the probability of event A and multiply it by the probability of event B. And this is only if they're independent. That would be if event A and B are independent. If the events are dependent on each other, such as the chip example, then we're going to have what's called conditional probability. So we would find the probability of event A and event B by taking the probability of event A and multiplying it by the probability of event B happening, given that we already know that event A has happened. So this little line here means given. This symbol here, or this notation here, means the probability of event B given that event A has occurred. Now, we could also switch the letters around, and it could also be calculated by saying the probability of event B times the probability of event A given that B has already happened. You can use either one of those formulas. If we go back to our example with our bucket with blue and red chips, let's say I want to find the probability that I pick a blue chip and then a red chip. So using this notation that we just learned, what I want to do is I want to find the probability that I got a blue chip and then multiply it by the probability of getting a red chip given that I already picked a blue chip. So on my first pick, if I picked a blue chip, remember we have 10 blue chips and 10 red chips. So if I pick a blue chip, that's a 1/2 probability on the first pick that I get a blue chip. But when I go to pick the second chip, the probability that I'm going to get a red chip is now 10 out of 19 because I already pulled a blue chip out. There's still 10 red chips left in the bucket, but I only have 19 chips in total. So that probability has changed. So if I pick a red chip on the second try, that's a 10 out of 19 chance. And when we multiply 1/2 times 10 over 19, we are going to get 0.2632. So I would say that the probability of getting a blue chip and then getting a red chip is 0.2632. Now we're going to move on to OR statements. Now when you're using OR statements and you're trying to find the probability of event A or event B happening, we're going to use addition. So the formula for OR statements, I would have the probability of A or B happening would be equal to finding the probability of event A happening plus finding the probability of event B happening, and then we're going to subtract off the probability of event A and event B happening. So this part here is a little confusing at first, but once you go through some examples, it will make more sense. But what this is saying is if there's any overlap in the probabilities of A and B happening, we want to subtract that to make sure that we're not counting any overlap twice. And like I said, that will make more sense once we go through some examples. So for right now, just make sure you understand that this is the formula that we're going to use for the probability of A or B. So now I'm going to show you some diagrams that will be like a visual tool for you so that you can conceptually understand what's going on here with the and the or statements. If you have two events, A and B, I'll label A with the blue circle and B with the red circle. If you notice, A and B don't overlap. There isn't the probability that event A and event B can happen at the same time. There's no intersection. So in this case, I would say the probability of A and B is 0. There's no overlap. There's no chance of both of those events happening at the same time. However, if there is overlap, so if I give you A in blue and then I give you the event B in red, this area here where they overlap will represent the probability that A and B happen. So I'm going to label that here. This area here where they overlap is the probability that A and B happen. Now remember, just a quick refresher, if the events A and B are independent, then you take the probability of A times the probability of B if you're trying to find the probability of A and B happening. If the probabilities are dependent, then you're going to take the probability of A and multiply it times the probability of B happening, given that we know A already happened. And then remember, you can reverse the letters and it would be the same probability. It's also equivalent to the probability of B happening times the probability of A happening, given that B has already happened. So this column here is a quick summary of all of our and information. Now let's go through the or statement. If I have an event A and I have an event B, and it's set up where there is some overlap. So when I shaded A, I shaded this area once. And then when I shaded B, because B overlaps with it, then I shaded that area again with B. So this area in here, again, represents the probability of A and B happening. If I want to find the probability of A or B happening, I'm going to use the addition rule. I take the probability of A, which is in blue, and I want to add it to the probability of B. But if you notice, that area in the middle was counted twice because the probability of A and B overlap there. So we don't want to count that area twice or that probability twice because that won't give us an accurate probability. So when we find the probability of A or B and there's overlap, that is why we subtract off the probability of A and B. So that area isn't counted twice. Now, we could have a situation where we have an or statement that is mutually exclusive. And mutually exclusive means there's no overlap. It is impossible for event A and B to happen at the same time. An example of two events that are mutually exclusive would be, consider birthdays. You only have one birthday. So it's impossible for you to say there's an event that I have a birthday in May and then there's an event that I also have a birthday in July. That's impossible. So when we have mutually exclusive events, there's no overlap. So I get this picture here. So that means when I find my probability of A or B, I take the probability of A plus the probability of B, and I subtract off any overlap. Since in the case where the two events are mutually exclusive, that overlap doesn't exist. So the probability of A and B is going to be 0. So when you have mutually exclusive events, your probability of A or B is just going to be the probability of A plus the probability of B. Because if you go to subtract off the overlap, there is none. So you can just add the probability of the two events if the events are mutually exclusive, meaning it's impossible for them to happen at the same time. Okay, so let's walk through some examples now. What is the probability of rolling 3 6s in a row with a single die? So we want to find the probability that we get a 6 on the first roll, and a 6 on the second roll, and a 6 on the third roll. Because we're using and statements here, the first thing we need to do is determine if these events are independent or dependent. We know we're going to have to multiply, but the question is, are we going to have to use the conditional probability, or are we just going to have to multiply the probability of the events together? So when I roll the first die, if I get a 6, that is not going to affect the probability of getting a 6 on the next die. So I would say that these events are independent. Which means to find the probability of the and statements, if they're independent, you just multiply the probability of the events happening together. So I want to find the probability of getting a 6, and then I want to multiply it by the probability of getting another 6, and then I want to multiply it by the probability of getting another 6. So the probability of getting a 6 is 1 out of 6. So I multiply that all together and I get 1 out of 216. That's my probability, 1 chance out of 216 of getting 3 6s. A 3-person jury must be selected at random from a pool that has 6 men and 6 women. What is the probability of selecting an all-male jury? Well, we want to find the probability of getting a male on the first try, a male on the second try, and then a male on the third try. I'll put a little 1, 2, and 3 down at the bottom to remind us that those are our first, second, and third picks. Now, are these events independent? This is an and statement, so we have to determine, is it dependent or independent? If I have 6 men and 6 women in a room, and I pick one, and then I go to pick another out of that room, the probability has now changed. If I pick a man the first time, then the chances of picking a man has changed again, because now it's out of 11 people rather than out of 12. So I want to take and find the probability of getting a male on the first try. And then I want to multiply it by the probability of getting a man on the second try, given that we had a man on the first try. Then I want to find the probability of a third man, given that we picked a man on the first and the second try. So the probability that we pick a man the first time is 6 out of 12, or 1/2. Because we have 6 men and 6 women. So now, if I pick a man out the first time, now I'm left with 5 men and 6 women. So when I go to pick a man the second time, I'm going to have a 5 out of 11 chance of picking a man the second time. If I pick a man the second time, then I'm only left with 4 males in the room and 6 females. So if I pick a man the third time, then it's going to be 4 out of 10 chance that I pick a man the third time. Now, when I multiply all that together, I get 0.091. So the probability of picking 3 men when you have 6 men and 6 women is 0.091. And we use conditional probability here because these events were dependent. Okay, the next example. Suppose you roll a single die. What is the probability of rolling either a 2 or a 3? So now we're getting into or statements. I want to find the probability of getting a 2 or getting a 3. The question is, with or statements, are the events mutually exclusive? Is there going to be any overlap that we need to worry about subtracting? So with or statements, we want to find the probability of 2, the probability of getting a 3, subtract any overlap. So that would be the probability of getting a 2 and a 3. Well, the probability of getting a 2 when I roll a die is 1/6. When I roll one die, the probability of getting a 3 is 1/6. Now the question is, if I roll one die, and here's the key word here, I roll it just once. If I roll it just one time, can I get a 2 and a 3? That's impossible. These events are mutually exclusive. You can't get a 2 and a 3 when you only roll a die once. So the probability of getting a 2 and a 3 would be 0. So I don't have to worry about calculating that. So I'm going to take 1/6 plus 1/6 and add them together. And that gives me 2/6, which is 1/3. So the probability of rolling a 2 or a 3 when you just roll one dice is 1/3. Next example, suppose you have a standard deck of 52 cards. Find the probability of drawing either a queen or a club. I want to find the probability of getting a queen or a club. With or statements, we use the formula, the probability of getting a queen plus the probability of getting a club, and then we minus any overlap. So the question is, are these events mutually exclusive? Can I get a queen and a club at the same time if I pick a card from a standard deck of 52 cards? The answer is yes. I can pick a queen and a club at the same time. So these events are not mutually exclusive because we do have some overlap. You can have a queen and a club at the same time. So when I go and pick a card out of a deck of 52 cards, I have a chance of 4 in 52 to get a queen. Right? There's 4 queens in a deck. The queen of clubs, the queen of hearts, the queen of diamonds, and the queen of spades. When I pick my card, the probability of getting a club is 13 out of 52 because there are 13 clubs in the deck of 52 cards. However, when I calculated this probability, that includes the Queen of Clubs. I counted the Queen of Clubs in this probability. I also counted the Queen of Clubs and the probability of selecting a club. The Queen is one of those 13 cards. So I just counted the Queen of Clubs twice. This is what we're talking about, overlap. I don't want to count the Queen of Clubs twice. So I want to subtract off the chance of getting a Queen of Clubs, which would be 1 out of 52. Now, when I put this in on my calculator, and I put in 4 out of 52 plus 13 over 52, and then I subtract 1 out of 52, that gives me approximately 0.308. So if I pick randomly out of a deck of cards, the chances of me picking a queen or a club would be 0.308. Next example, the following 8 people are in a room. We have 2 Democratic men, 2 Republican men, 2 Democratic women, and 2 Republican women. If you select one person at random from this room, what is the probability that you will select either a woman or a Democrat? I suggest when you're given a lot of information like this, that you organize the information in a table. So we have men, we have women, and we have Democrats and Republicans. Okay, so it says I have 2 Democratic men. So that's going to go in this box here. I have 2 Republican men, so that's going to go in this box here. I have 2 Democratic women, so that's going to go here, and 2 Republican women. So that means I have a total of 4 men, 4 women, and a total of 4 Democrats and 4 Republicans. And overall, that means I have a total of 8 people. So I want to find the probability of getting a woman or a Democrat. The fact that I'm looking for the probability of an or statement tells me that I'm going to use the probability of getting a woman plus the probability of getting a Democrat, and then I subtract off any possibility of overlap. So the probability of getting a woman and a Democrat, so that we don't count them twice. The probability of getting a woman is 4 out of 8. If I look at this woman column, there's a total of 4 women out of a total of 8 people. So I'm going to write the probability is 4 out of 8. Then I'm going to add that to the probability of choosing a Democrat. There's 4 Democrats out of 8, so I'm going to add plus 4, 8. But I want to subtract anybody that was counted twice. If you notice, then these 2 people here were counted twice. I counted them in the Democrat probability, and then I also counted them in the probability of choosing a woman. So I don't want to count those 2 people twice, so I'm going to subtract off 2 out of 8 to make sure they're not counted twice. So when I put 4 over 8 plus 4 over 8 minus 2 over 8 in my calculator, I am going to get 0.75. So the probability of selecting a woman or a Democrat is 0.75 or 75% chance. The last topic I want to cover with you in this lesson is the at least once rule, and this only works for independent events. So if I want to find the probability of at least one event A in n trials, there are two formulas I can use for that. Whoops, that doesn't look like a very good n. N trials. The formulas that you want to use for that, there's two of them, and it doesn't matter which one you use. They'll both give you the same answer. However, sometimes you'll have information for one of the formulas and not the other. So you'll just have to look to see what information is given to you in the problem so you can decide which formula to use. But the two formulas are 1 minus the probability of no event A in n trials. And the other formula is 1 minus the probability of no event A in one trial, and you raise that to the nth power, and then subtract from 1. Okay, so let's practice using these formulas. In the first example, it says find the probability of at least one head when you toss 3 coins. So the number of trials is 3. You're tossing the coin 3 times. So we can use, in this case, both formulas. I'll show you how to use both of them, and then you can see that they both work out the same. We have enough information to use either one of those formulas. If we use the first formula, I would have 1 minus the probability of no heads in 3 trials. If I get no heads in 3 trials, that means I'm going to get all 3 tails. So I'm going to get tails, and tails, and then tails. That would give me no heads in 3 trials. Well, I have a 1/2 chance of getting tails the first time. Then I have a 1/2 chance of getting tails the second time. And then I have a 1/2 chance of getting tails the third time, which would give me a 1/8 chance of getting no heads in the 3 coin tosses. So I'm going to take 1 minus the probability of no heads in 3 trials, which is 1 minus 1/8, which would give me 7/8. So the probability of getting at least one head when I toss the coin 3 times. If I use the second formula, I would use 1 minus the probability of no heads in 1 trial. And then I would raise it to the nth power, which is n would be the number of trials. So the probability of no heads in 1 trial would be 1/2. If I flip a coin and I get no heads, that means I get a tail. Well, the probability of getting a tail is 1/2. So the probability of getting no heads in 1 trial would be 1/2. And I have to raise that to the 3rd power. So I would take 1 minus 1/8, because 1/2 times 1/2 times 1/2 is 1/8, and I would still get 7/8. The big difference between these two formulas that I want to point out is that in the first formula, it's talking about the probability in all the trials, and in the second formula, it's talking about the probability in just 1 trial. Okay, one more example. It says you purchased 10 lottery tickets for which the probability of winning some type of prize on a single ticket is 1 in 10. What is the probability that you will have at least one winning ticket among 10 tickets? So let's break this information down. We got 10 lottery tickets, so that means we've got n trials. We've got n chances to win. it says the probability of winning on a single ticket, so in one try, is 1/10. So the probability of winning in one trial is 1/10. What is the probability that you have at least one winning ticket among the 10 tickets? So we want to find the probability of at least one winning ticket. Now, if we scroll back up and look at our formulas, in order to use these formulas, I need to know one of two things. I either need to know the probability that I don't win in 10 trials, because we're talking about 10 tickets, or I need to know the probability that I won't win with one ticket. Well, we have the information for the second formula, but not the first. The second formula says I'm going to take 1 minus the probability of no wins in one trial, and then I want to raise that to the number of trials. The information that was given to me that in one trial I have a 1 in 10 chance of winning. So that means in one trial I have a 9 in 10 chance of not winning. So that means my probability of no wins in one trial would be 9/10. And I would have to raise that to the 10th power because my n is 10. I have 10 trials. So when I put that on my calculator, I'm going to get approximately 0.651. So I have a probability of 0.651 to win at least one ticket in 10 tickets.